When in 1740 King George II asked the Royal Society to study the physics of cannon fire, it fell to mathematician Benjamin Robins to carry out the field trials. One of the questions Robins sought to resolve was how far a cannonball would carry for any given quantity of gunpowder. Painstakingly, he measured out larger and larger amounts of explosive, and, as might have been expected, the more powder Robins used, the further the shot carried. Eventually, however, he ran into an unexpected phenomenon. Beyond a certain charge, the cannonballs ceased to carry as far as they should. With extraordinary insight, he concluded that air resistance was the problem. Unwittingly, he'd discovered the sound barrier. What he didn't realize was that his cannonballs were now traveling supersonically. What would Benjamin Robins have thought of the proposition that one day human beings would cross the Atlantic in machines traveling at twice the speed of his cannonballs? For the last 15 years now, almost as a matter of routine, hundreds of airline passengers have been crossing the Atlantic every day, 10 miles above the Earth, at twice the speed of sound. Hurtling through the air at the rate of 1 mile every 2 3/4 seconds, only a thin aluminium shell separates them from a hostile environment. Despite the numbingly cold air temperature at this height, the airflow over the aircraft's skin heats it to more than the boiling point of water. In part, this heat is created by friction with the air molecules in the atmosphere. But the heat is also created because Concorde is simply moving too fast for the air ahead to get out of the way, and so the air is compressed into a system of hot shock waves. These shock waves of compressed air radiate out in all directions from the aircraft and are the cause of the characteristic sonic boom that sailors hear when crossing the Atlantic by somewhat slower means. The shock waves and their associated boom is the reason Concorde is prohibited from flying supersonically over populated areas.
A shock wave is rather analogous to the bow wave of a boat. If for a moment you can imagine a series of fishermen along a bank of a canal, each would get his feet washed by the wave as the barge goes past.
Now, shock waves always travel at the speed of sound, whatever the speed of the object that's creating them. This fact provides aero engineers with an alternative and more useful unit of speed, the Mach number, named after the Austrian aerodynamicist Ernst Mach. Mach 1 is the speed of sound, Mach 2 twice the speed of sound, and so on. Any object traveling faster than Mach 1 creates a shock wave, but not all objects create them in the same way. A streamlined shape like Concorde produces less powerful shock waves than an unstreamlined shape like Benjamin Robins' cannonball. That's why modern bullets are the shape they are, to overcome the drag that Robins encountered and carry further. In aviation, streamlining an aircraft to reduce drag enables you to fly faster for the same amount of power. But as they discovered in World War II, for as long as that power is driving a propeller, there's a limit to how fast you can go. The problem is that if a propeller blade approaches the speed of sound, it will of course develop shock waves. The resulting drag will not only destroy the propeller's thrust, but may also transform the spinning disc into a huge air brake. It became clear that to travel supersonically, you need a supersonic propulsion system. If you get your sums right, you can make the gases leaving the nozzle of a rocket move supersonically. Unfortunately, Hitler's rocket technologists did get their sums right, and their supersonic V-2 missiles devastated communities that quite literally never heard them coming. The Germans applied this rocket expertise to the production of a new fighter, the Messerschmitt 163. It was a delight to fly, although it did have a few unfortunate tendencies. It could only carry enough propellant for 12 minutes of powered flight, after which it became a glider. To save weight, the pilot had to jettison the undercarriage on takeoff, which made landing an occasionally backbreaking procedure. And if this wasn't enough, there was another unexpected problem associated with the 163. If you weren't careful, you could accidentally stray too close to the mysterious sound barrier.
This aircraft, the ME-163, could be flown and maneuvered at a Mach number of 0.82 in an era when there were few Allied fighters that could be maneuvered much above 0.72. So it was really untouchable as regards speed by any enemy fighters. However, it did provide a problem for the pilot. If it reached a Mach number of 0.84, was at its absolute controllable limit. If it was taken a fraction beyond that, it went into what can only be called a graveyard dive. There was no way out of it. It was such a tuck-under dive that it was inevitably a fatal crash.
The operational limitations of chemical rockets encouraged Germany to look for an alternative power source. They found it in the newly invented jet engine. The result was the shark-like Messerschmitt 262, a frightening and highly dangerous sight to any pilot who fell foul of one.
The Me-262 was the most formidable aircraft of World War II. It appeared not long after the Me-163, and it was fitted with two axial flow jet engines. Yet this aircraft had a limiting Mach number of 0.86, but a tactically usable Mach number of 0.83. And this is at a time when Allied fighters had only tactical Mach numbers in the region of 0.72, 0.74. So the Me-262 was, in effect, untouchable.
Untouchable, that is, so long as it worked. For despite the 262's advanced airframe, its new jet engines lasted only 10 hours apiece and were notoriously unreliable. At around the same time, jet technology was also being developed in England, and prototype aircraft like this curious-looking Gloucester Whittle were put through their paces. These new high-speed jets were immensely attractive to the RAF, who were having a hard time intercepting Germany's V-1 flying bombs. So in 1944, 616 Squadron's Gloucester Meteors became the first Allied jet to see active service. Once the urgency of war had finished, the race to break the sound barrier began in earnest. In the California high desert at Muroc Air Base, the Americans had elected to use the raw power of a chemical rocket to challenge the sound barrier with the Bell X-1. Owing more to an artillery shell than an aircraft for its shape, it was a no-apologies, no-nonsense, brute-force rocket plane with but one objective: break the sound barrier. It was easier said than done. In October 1947, as the X-1 approached the speed of sound, Air Force pilot Chuck Yeager knew that for a brief moment his controls would be unresponsive. The engineers had told him that shock waves forming on the wings and tail would be responsible for the unwelcome effect. He continued to accelerate the aircraft, and to his relief, his controls began to work again. Yeager had broken the sound barrier. In Britain, the same problem was dogging the trials of another new jet, the de Havilland Swallow. The Swallow is said to have been inspired by the Me-163, and it embodied a number of design features first developed by the Germans, including swept wings. Unfortunately, the pretty little Swallow was an ill-fated aircraft. 3 were built, and all of them fell out of the skies, killing their pilots. It seemed that just as the Swallow copied the design of the Me-163, so it also faithfully copied its graveyard dive. The problem stemmed from the way a wing behaves when traveling near to the speed of sound. A wing generates lift because the air traveling over the top surface is forced to move faster and is at a lower pressure than the air passing under the bottom surface. When the wing is moving very fast, however, the air flowing over the top surface is forced to travel supersonically, and the result is a high-pressure shock wave seen here in red. It's this shock wave that aircraft designers have to worry about. If
you don't design your aircraft properly, the effect of the shock waves on the controls can be highly dramatic and totally undesirable. For instance, the shock wave will build up and put a wedge of high-pressure air over the control surfaces, with the result that it would make them almost impossible for the pilot to move, or worse still, to make them flutter like a flag in a stiff breeze.
These were the effects that had proved so fatal for the Swallow and the 163. Although, as Jaeger had been fortunate enough to find out, once an aircraft passed through the sound barrier, the shock waves would establish themselves on the trailing edge of the wing, where they could do less harm. As aerodynamicists began to understand what was going on near the speed of sound, it became clear that swept wings were to be a key feature of high-speed flight. With swept wings, the oncoming air behaves as if it were meeting a broad, thin wing, and thin wings are good news. The troublesome shock waves that build up on the upper surface of a fat wing don't occur until much later if the wing is thin. For these reasons, the world's first Mark II jet, the Lockheed Starfighter, had extremely thin wings, which were only inches thick even at the wing root. As research into supersonic flight progressed, a new and elegant shape began to take to the skies, the now familiar delta wing.
The Fairey Delta II had made another breakthrough. It was a delta. That meant that the wingtips were within the shock wave generated at the nose, and equally it was a slender delta, which meant that the air, which still has to be parted, was parted a little bit more gently than would have been the case with a straight-winged aircraft.
During the 60s, the Fairey Delta was used to pioneer a number of aeronautical innovations which were to influence the design of Concorde. Different wing shapes, the extensive use of hydraulically powered control surfaces, and the familiar drooping nose were all test-flown on this aircraft. But still, the Fairey Delta was essentially a military-style plane. How different would a supersonic civil airliner have to be?
I think the difference comes out in the need for the civil aeroplane to have a long life, to have very good fatigue characteristics, and of course for the people to be comfortable in flying in the aeroplane. They're not pilots after all, they're just you and my grandmother. So that you have to aim for a very normal existence in a civil aeroplane, whereas you can have rather a special existence in a military one.
When Concorde entered airline service in 1976, Britain and France were collectively £2.5 billion poorer. But that money had purchased a measure of scientific and technological expertise in supersonic civil aviation that is still preeminent nearly 2 decades later. It hadn't simply been a matter of achieving Mach II. It had to be done safely, economically, routinely, without spilling the gin. Climbing towards 29,000 feet and Mach 1, the transonic speed range so fatal to the early pioneers, the throttles are pushed forward and the afterburners lit to nudge the aircraft through the sound barrier. On the flight deck, the pressure-sensitive instruments register the passage of the shock waves down the fuselage as the aircraft penetrates the sound barrier. For the passengers, there is a slight jolt as the afterburners are lit, and a discreet display modestly informs them of the fact that they have passed the speed of sound. Because the lift over the wing changes as the aircraft becomes supersonic, the tendency for the nose to dip is countered by moving the aircraft's center of gravity backwards. This is done by pumping 12 tons or so of fuel from the nose of the aircraft to its tail. Using the unburned fuel as ballast isn't its only job on Concorde. It's also used as a coolant. 2.5 hours of supersonic flight generates a lot of heat. This could overheat both the systems on the aircraft and the passengers. So, using heat exchangers, Concorde dumps this unwanted thermal energy into the fuel on its way to the engines. Inside the cabin, the only unusual aspect of supersonic flight is the fact that the windows are decidedly warm. Inside the engines, it's a very different story. To work at all, the 4 Olympus engines on Concorde need to be fed subsonic air, even though the aircraft is flying supersonically. Like the propeller on a World War II fighter, the compressor blades at the front of each engine simply couldn't cope with supersonic air. Shock waves would form and starve the engine of oxygen. To get around this problem, doors in the intakes close during supersonic flight to create a cascade of shock waves upstream of the engine, slowing the incoming air from 1,300 to 300 miles per hour. This remarkable exercise has the added benefit of compressing the air even before it enters the engine, thereby improving the thermal efficiency of the propulsion system. But despite its technical brilliance, today Concorde is undersized, has a very limited range, and costs over £4,000 to fly to New York and back. So what improvements would need to be developed before we could expect to see its successor?
The question is the technology there to deliver the goods at a price which is reasonable for the passenger? The sort of problems we've got to solve, first of all, we've got to have a bigger aircraft, maybe a 200 or 300 seater. We've got to have a quieter aircraft. For that, you would have engines with a variable cycle, engines which would behave like the efficient jumbo jet engines when going slowly and like the efficient Concorde engines when going quickly. And on top of that, you need to tweak up the aerodynamic efficiency.
Technology has to move to give us an aircraft that's efficient enough for the airlines to make some money, and at fare levels that people can afford, fairly ordinary fare levels. So technology has to move to meet that standard. But it has moved. It's moved very substantially. And I don't think we're talking about developments which are impossible.
But such developments require political as well as commercial will. And, as was seen in the USA in 1972, when the American SST was cancelled, even mighty Boeing couldn't overcome the combination of commercial and environmental resistance.
I think one of the worst things that's happened to Concorde was that the Americans decided not to do a supersonic airplane. Because if they had done a supersonic airplane, even though there would have been pretty tough competition, there would have been a constituency on each side of the Atlantic who wanted it to happen. So transatlantic rivalry, or the transatlantic situation, was really pretty important. Environmental pressures were also important, but I would have been much happier with Boeing staying in the scene than the fact where Boeing dropped out of it. In the days of Concorde, we had lots of environmental problems. In an environmental situation which wasn't all that well understood, it was the beginnings of concern, if you like, and Concorde was rather an important example of an aircraft that was noisy and might do some damage in the upper atmosphere. And the Concorde problem was, to a large extent, solved by only being 14 of them in service. But there wouldn't be only 14 of a new second-generation aeroplane. We hoped there'd be quite a lot so that it was a commercial proposition. I think we can come up with a power plant design which will meet the subsonic requirements, and we can do it with a little bit of margin so that we've got confidence to go ahead. For the upper atmosphere effect, we have to know a little bit more about the atmosphere and how a supersonic aeroplane would affect it, and to try and assess whether it would do any damage.
And that's the crucial question for a second-generation supersonic aircraft. Can it be demonstrably ozone-friendly? If it can't, you're looking at a museum exhibit. Even if it can, the future's still uncertain.
I don't think the bet would be better than 50-50 at the moment. But with a technology base which is improving all the time, that's not a bad bet.
The civilian marketplace now realizes that shock waves cost money. So, if quieter, cleaner SSTs are to be built, they will also have to fly further to service the fast-growing economies of the Pacific Rim. But some aviation analysts are asking, is Mach 2 fast enough? Many countries are designing aircraft that would go beyond supersonic speeds into what are called hypersonic speeds. That's more than 5 times the speed of sound. France has plans for a Mach 4 Avion de Grande Vitesse, or AGV. Germany has plans for the Mach 5 Sänger, which can be either a hypersonic airliner or the first stage of a high-altitude shuttle launching system capable of firing a small spacecraft called Horus into Earth orbit. It's as if the rules of physics are saying, the faster you fly, the higher you go. Does this mean then that you could fly straight into space? 3 years ago, some very important people thought it did. They even had a name for it, the New Orient Express.
So yes, this nation remains fully committed to America's space program. We're going forward with our shuttle flights. We're going forward to build our space station. And we're going forward with research on a new Orient Express that could, by the end of the next decade, take off from Dulles Airport, accelerate up to 25 times the speed of sound, attaining low Earth orbit, or flying to Tokyo within 2 hours.
The President rather jumped the gun with his Mach 25 vision, since we don't even have the technology to build a Mach 4 aircraft. Currently, the fastest plane in the Western world is the Mach 3.5 Lockheed Blackbird. At speeds in excess of 2,300 miles per hour, at an altitude of over 95,000 feet, its skin temperatures exceed a blistering 300 degrees centigrade. To withstand these temperatures, the whole aircraft is pre-chilled and filled with refrigerated fuel before takeoff. The Blackbirds were ordered by the CIA in 1959. They first flew in 1962 and were unveiled to a startled public in 1964. Since then, their phenomenal speed has enabled them to outrun missiles over Russia, China, and Vietnam. But they're far from being the fastest planes ever built. That particular accolade belongs to one of the proud successors to Chuck Yeager's Bell X-1, the hypersonic North American X-15.
Here's coming on now. Real slow to pick up hydraulic pressure. 3 minutes to drop. Line to jettison. Most looking good. Hey, Scotty, you ready? I'm ready when you are, buddy.
The X-15 program was arguably one of the most successful ever, performing 199 research flights from 1959 to 1966, setting speed and altitude records and earning the pilots the title the first spaceman. It was a true experimental aircraft. The successes of later flights were built upon the lessons of the earlier ones. Of the first 45 flights, at least a third would have resulted in the total loss of the vehicle if there had not been a pilot on board to save it. North Americans Scott Crossfield had the task of testing the 3 production X-15s before delivery. He had his fair share of incidents and learned the truth of the old adage that if you can walk away from it, it was a good landing. But even testing the X-15 on the ground had its hazards.
Prior to flying the airplane with the first big engine in it, which was a 60,000-pound thrust rocket engine, I get in the cockpit to make a ground run and everybody else gets into blockhouses. That's called building the confidence of the pilot. Well, on this ground run, which is the last ground run we were to make before the first flight, the airplane blew up.
Throttle off. Reset.
And it blew the front end of the cockpit and the instrument bay of the airplane about 20 or 30 feet forward. And I claim that's the shortest, highest thrust flight ever made by man, and they never would have let me log the time. But anyway, it was like sitting in the sun. And in this very bright orange surrounding me, the fire truck began to move in and began to get dark with just a wall of water in front of it. And in the bottom of that wall of water was one of my mechanics. Art Simone was his name, and I still choke up a little bit because he was coming into that Holocaust risking his life to save mine. and I'm in a very well-designed temperature-resistant structure. He's out there in that fire. Well, I tried to wave him away, and he wouldn't go away. He tried to open the canopy, and I could see his fingers were searing on the hot fuselage when he tried to get the handle open. So the only choice I had, since he wouldn't stop doing that, was to open the canopy, and I didn't want to crawl across that hot fuselage, so I jumped out and landed on top of him. We rolled in the water and got all wet and ran out of there. Really none the worse for wear except the burns on his hands. Before we could call the factory and tell them that we'd just blown up a $50 million airplane, the newspapers started calling. And I wanted to calm them down, and I said, hey, relax. The only casualty was pressing my trousers when the fireman got me wet. And then, of course, I winced when I realized what I'd given the bastards. And so, sure enough, the next day, an East Coast newspaper had a headline, X-15 blows up, pilot wets pants.
During the 60s, the hypersonic X-15 program continued to notch up record after record. X-15 test pilots flew to heights of nearly 70 miles above the Earth at speeds approaching 7 times the speed of sound. But even as the hypersonics program was venturing carefully into space, the politicians were about to reach hungrily for the stars.
I believe that this nation should commit itself to achieving the goal, before this decade is out, of landing a man on the moon and returning him safely to the Earth. No single space project in this period will be more impressive to mankind or more important for the long-range exploration of space, and none will be so difficult or expensive to accomplish.
Godspeed, John Glenn.
Kennedy's 1962 speech effectively killed the hypersonic X-15 program. For despite the outstanding achievements of the pilots who flew them, these were not spacecraft, they were aeroplanes. The urgency of Kennedy's declaration opened the door for the missile men. The expendable rocket offered a short cut down the road to Tranquility Base.
2.5 down. Straight shadow. 4 forward. 4 forward. Drift into the right a little. Ready? Down a half. 30 seconds. Forward. Good. Ready? Contact light. Okay, engine stop. We copy you down, Eagle. Listen, Tranquility Base here. The Eagle has landed.
So the X-15 program and the research airplane program grew to a halt just from neglect as we went out and did what I call the NASA spectaculars. Now, nobody's going to knock going to the moon. I just wish that we had done it in the logical steps of putting a permanent U.S. man present in Earth orbit first, creating a facile way to get back and forth to there, and then moving on. If we had done that, we would be at a stage now where we would be truly in a position and a posture to go to Mars with men if we wanted. But we didn't. We shot from the hip in a half a dozen different directions.
Since Skylab, there's been no permanent Western presence in space, and it's now 20 years since men last strolled across the lunar landscape. It seems as if the political expediency that spawned the manned space program has proved just as capable of killing it. Today, it's the shuttle that is the politicians' new victim.
The shuttle program was actually a program run by the Congress of the United States. They made the decision. NASA came with a fully reusable two-stage, both manned vehicle, rather like the Horace Sanger, except it was stacked differently. And this vehicle would have been perfect. The Congress said, no, it's going to cost $10 billion. That's much too much. You can have half of it. Go back to the drawing boards. They went back to the drawing boards, and they came up with this strange witch's broomstick tied to a stick of dynamite that they've got at the present time. That was not the way to go.
It costs $5,000 to take a single kilogram of payload into orbit on the shuttle. and an army of 20,000 technicians are needed for every launch. On takeoff, around 80% of the weight of the propellant is liquid oxygen, and within 6 minutes, most of that will have been burned as the vehicle punches out of the Earth's atmosphere. An air-breathing hypersonic spaceplane that could fly into orbit and return at will would clearly be an attractive proposition, if it could be achieved.
In order to fly an airplane from the ground to orbit, first of all, you have to design an airplane that will take off and land like a relatively conventional airplane. You have to design an airplane that is sufficiently lightweight that it can carry the fuel required to accelerate from 0 speed to orbital speed, which is around 17,000 miles per hour. In order to do that, the materials have to be light, they have to be strong, and they also have to be able to withstand an extremely high temperature.
The British Horizontal Takeoff and Landing Project, or HOTOL, is the simplest of the spaceplane designs. It is an air-breathing rocket with wings, which takes off like an aeroplane from a conventional runway. Unlike a conventional aeroplane, however, HOTOL has been conceived from its inception as an unmanned spaceplane.
HOTOL, of course, was conceived as an unmanned vehicle very deliberately. There are many reasons why you don't want a man on a vehicle like HOTOL. HOTOL's designed to meet an unmanned spacecraft traffic market. It's communications satellites and scientific satellites, all sorts of application satellites. And the man only goes for a ride. So if you can leave him behind, you've saved the weight of the man and his life support system. You've reduced the development cost of the aircraft because of the possibility of relaxing safety standards to some degree. And also you've removed the necessity to develop the manned life support system. So for a first generation vehicle, then there really is no need to put a man on HOTOL. And as a result, the development cost of it is more or less halved.
Everyone agrees that the clever bit about HOTOL is its engine. It's a fairly conventional rocket motor which has been adapted to use the oxygen in the air through which it's passing. In such an engine, very cold liquid hydrogen, shown in green, is pumped through a heat exchanger in the air intake. This heat exchanger cools the incoming air until it almost liquefies. This freezing air is then pumped with the liquid hydrogen into the rocket motor. As HOTOL leaves the atmosphere, it switches over to a small inboard store of liquid oxygen for the final push into orbit. Using atmospheric oxygen in this way saves a lot of weight.
The HOTOL vehicle, when it takes off, has something like 100 tons of liquid oxygen on board and of the order of 60 tons of liquid hydrogen. If that was a more conventional rocket, then the amount of liquid hydrogen would have remained about the same, 60 tons. But now you'd have something like 360 tons of liquid oxygen on board. So by going to the HOTOL type engine, you've saved the necessity of installing 260 tons of propellants actually in the vehicle at launch.
Bond believes that the relative simplicity of the unmanned HOTOL concept, combined with its promising economics, will make access to space sufficiently cheap for other types of mission to be developed.
One could see, for example, a version which would be simply passenger carrying, to carry people into space to space stations and back to Earth on regular servicing missions and so on. One can see pure tanker versions of HOTOL for the purpose of carrying propellants into space efficiently. And then, of course, developments of the cargo version. But also somewhere in the distant future, when the hydrogen technology is pretty well mastered, then the possibility of civil transport by ballistic airliners based around HOTOL-type concepts may well be feasible.
But HOTOL is still only a paper concept, and the British government have said they will not fund its development. So, despite the hope that it could one day bring payload-to-orbit costs down to as little as 1/10 of the current shuttle costs, the future does not look rosy for HOTOL.
I have to say that British Aerospace have been very bullish about HOTOL right from the beginning. There is a lot of faith within the company about the HOTOL project and about the necessity of the vehicles. You have to remember that the area of British Aerospace where HOTOL was originally conceived, is connected with satellites. Their main business is producing satellites and selling them. And they see the limitations on the future as being the cost of getting a satellite into orbit. So they feel very strongly that vehicles of this sort are necessary. Now, the realities of funding have, I think, probably forced a change of strategy on them. And today's HOTL project is much more of a technology project of a generic sort, rather than specifically HOTL type of studies. But again, that should give British Aerospace the necessary technology base to eventually join projects, European or even other nations' projects, and keep some British investment in that.
Over in the United States, former President Reagan's Orient Express is now known as the National Aerospace Plane, or NASP. By calling it the Orient Express, Reagan implied a civil function to which it has never really aspired. The NASP is in fact an X-plane. Its designation is the X-30, and it's descended from the same ancestral line as the experimental X-1 and X-15. Already, test pilots are flying to orbit and back in the simulator to test the exotic systems that will be needed to make the real X-30 fly.
The mission for the X-30 is really to demonstrate technology. We're developing technology in this particular phase of the program, and we're really moving along quite nicely. We have a few more years to go, but we'll never be able to have the complete set of technology that we need to really convince people to build useful vehicles of aerospace planes and hypersonic vehicles. We have to go into that demonstrator, and that's what an X-plane is all about, and it will extend our technology database and really give us the risk, confidence that we need to go ahead with the aerospace vehicles of the future.
It's been said that those future aerospace vehicles will be as far in advance of today's space shuttle as Concorde is in advance of the Wright brothers biplane. The X-30 will need materials with new and quite remarkable properties. Seen here in a laboratory demonstration, this cube of silica insulation from the nose of the shuttle has been baked in a kiln at 1,100 degrees centigrade for 5 hours. Within seconds, its unique properties enable the technician to hold the cube in his unprotected fingers. And yet even this degree of insulation won't be good enough for the 17,000 mile/hour X-30.
The increase in the thermal requirements imposed by NASP have required a whole different type of materials from those we're familiar with. Whereas in the past we were able to get by with aluminums and finally higher temperature aluminums, the NASP requires even more exotic materials, such as titaniums, titanium aluminides, titanium composite materials, and very unique fabrication types of structures such as the honeycomb materials and so forth. One of the things we must do as we design the components for the NASP material is to worry about not only the strength of the materials, the stability of the materials, but the response of the materials under the thermal environment in which it must operate.
The whole X-30 concept hinges on the development of these new materials and the manufacturing methods needed to produce them. Already, metal hybrids are being developed with new and unusual crystalline structures. New alloys are being developed, which can withstand sustained exposure to the high temperatures of hypersonic flight. New testing procedures are also being devised, such as this 40-megawatt argon plasma wind tunnel, which will study the combined effects of temperature and aerodynamic load at simulated speeds of up to Mach 14. And new materials have been invented which can even withstand the alarming stresses of being alternately plunged in fluidized silica at 800 degrees centigrade and liquid nitrogen at minus 192 degrees centigrade. This bizarre and potentially explosive test will be used to assess those parts of the aircraft structure which come into contact with the scorching external airflow and which need to be actively cooled with the cryogenic liquid hydrogen fuel.
Now, the types of cooling that we use on the aircraft are mostly active. Some passive cooling, which is radiation cooling, that is, we radiate heat back out to space. But most of the heat is absorbed in the fuel that we're using, in this case hydrogen. And we must maintain the maximum temperature hotspots on the aircraft to within the material limitations, their capabilities. Not doing so, of course, will create burn-throughs. Burn-throughs will create losses of cooling flow, which could have even more disastrous effects. So we must be very careful in designing the cooling system of the vehicle so that it can survive and operate continually in the environment in which we're subjecting it.
The X-30 will not only be constructed from completely new materials, but will obey its own new aerodynamic rules. No one is saying what the final version will look like, but engineers are already trying to simulate how various configurations would behave.
In conventional airplanes, you have an engine that produces thrust, an airplane that produces lift. Hypersonically, you find that the engine now contributes to the lift of the airplane, and the airframe produces and contributes to the thrust of the engine. So they're not really inseparable. It's like an orchestra in which all of the pieces have to be playing the same harmony, the same music by an orchestra leader. And it's no longer possible for each piece to play its own tune.
It is in fact a flying engine, and we recognize it as such. But it's also an engine that has to keep its pointed end going forward. It has to be able to land, it has to be able to be maintained, and it has to be reliable. So it's an engine that operates like an airplane.
Unfortunately, no conventional wind tunnel facilities exist which can run continuously beyond Mach 8. It is possible to achieve very high Mach numbers, but only for a millisecond or two. Nevertheless, the information gleaned from these fleeting tests is fed into a computer in order that a mathematical model can be built of the aerodynamics of the projectile. This enables the scientists to assess the flight characteristics of any given shape without having to build it. In turn, this helps the designers to try out different possible hypersonic airframes and shapes in order to optimize the important characteristics of lift and drag, where the heating will occur over the surface of the aircraft, and how the air will flow into the engines.
The airplane is designed unlike any previous airplane we've ever designed. The whole forward portion of the airplane, it really has to function as an engine inlet. It has to function to gather the air and to efficiently compress it so that it will go into the engine. And that requires shaping the front end of the airplane in a very precise manner. In a similar fashion, the back end of the airplane has to function as a nozzle, much like a rocket nozzle, and that causes the back end of the airplane to look unlike anything that's ever flown before. So when you put those two things together, a very strange-looking front portion and a strange-looking back portion, you come up with an unusual-looking airplane.
The unusual look of the X-30 is due in part to the fact that it uses several different engines over its entire speed range. At slower speeds, a turbojet sucks in cold subsonic air, adds fuel, and generates a hot supersonic exhaust. But it won't work beyond about Mach 3, because the complex machinery inside a turbojet can't cope with the supersonic airflow. Ideally, you'd want to throw away the turbines and compressors and convert your engine to a ramjet, which is basically a hollow tube. Ramjets only work once you're traveling extremely quickly, relying on the forward speed of the aircraft to compress the air inside the engine. Burning fuel in this compressed airflow generates thrust. But at speeds above Mach 5, the air in the ramjet will be moving too fast for the fuel to burn efficiently. It's now time to change engines once again to a type known as a scramjet. In theory, this kind of engine would allow you to accelerate all the way up to Mach 15, although no one has yet been able to sustain the supersonic combustion for more than a fraction of a second. Computer models of a functioning scramjet suggest that the biggest problem is concerned with how to mix the fuel and the supersonic air without creating shock waves in the engine, shown here in red. After a certain point, however, the amount of energy you can add to the airflow passing through your engine by burning fuel begins to diminish. Surprisingly, perhaps, you can even reach a stage where burning fuel makes no difference at all.
I add fuel energy, and that overcomes not only the losses in the engine, but the drag of the airplane. And it is the fuel added to the air that makes thrust. Below all the speeds we've ever flown in now, that's true. When we start flying above 7,000 feet a second, now what happens is the incoming airstream has about the same level of energy as the fuel I can add. So it's still not too bad. If I just double the speed to 14,000 feet per second, I now only have the capacity to put in 1/4 the energy that is in the stream right now. So that if the process of the air flowing into the airplane, through the engine, and out the exhaust nozzle, if that process loses 1/4 of the energy of that stream, I get zero thrust.
Somewhere above Mach 15, scramjets will probably cease to provide any more thrust, and then the X-30 will switch to its fourth and last propulsion system to push it into Earth orbit, a small rocket motor. If the X-30 makes it into orbit, it will have surmounted a greater technological challenge than sending a man to the moon. But more even than that, it will also have had to overcome a great deal of political resistance from a Congress that continues to ask, why do we need the X-30?
When we crossed the continent at the turn of the 19th century, we were going from St. Joseph, Missouri to Sacramento in an expendable vehicle, just like we're going to orbit now, called a Conestoga wagon. Very few ever came back. If they did, they needed a great deal of rehab and maintenance. It did allow colonists to go out, but it did not allow for two-way trade. The two-way trade were the ships around the Horn. And it wasn't until the visionaries, the industries, robber barons, whatever you want to call them, the railroad people said, we need the government's cooperation, which they did by giving them land grants, and they proceeded to put in a pathway to the west, which was less dependent upon weather, schedulable, lower cost, non-expendable, and more importantly, the trade went both ways. Passengers could go one way, products, gold, cattle could all come back to the east. If we lose the X-30, we lose that vision of a railway to space, and we're going to be stuck with Conestoga wagons.
Commitment is the only thing that will get us through these kind of projects, but it is difficult, particularly when there are cycles, political cycles, budget cycles, and there's always a question of should we continue to do this or should we not. But it's long-term commitment that really gets you there. When you think of the man landing on the moon, it was a 7 or so year commitment through several administrations and many, many budget cycles, but we finally did it. I think we have to hope for that, we have to work for that, we have to stand ready to fight very hard for that kind of commitment.
In the final analysis, it isn't going to be the scientists that decide, and this program probably will not live or die on scientific grounds, it'll live or die on political ones. And here is where we've got really big gaps. We have not done the politics, quote unquote, that are required for this type of program.
The battle that David Webb and his colleagues face is going to be a difficult one to win. Like many previous X-plane programs, it will certainly be accused of being no more than the pursuit of technology for its own sake. In a way, this is true. The X-30 is a technology demonstrator, not the Orient Express. It has no specific mission to fill, no particular role to play, other than to find out what happens when you fly extremely fast. And that, argue the X-30's champions, is the point. Who knows what benefits may accrue from the X-30 research that is being conducted into exotic new materials, propulsion systems, or fluid flow computation. The truth, of course, is that nobody knows. Although, as Alan Bond, the inventor of the HOTOL engine, points out, that isn't necessarily a reason not to proceed with a project.
I think that funding on projects of this sort in the future has to come from city finance type sources and private investment, large institutions, that sort of thing. And I believe that a different view has got to be taken by those people of the actual economic value of something, even when it's perceived to have been an economic failure.
In some quarters, that's how Concorde has traditionally been viewed, a technological marvel but an economic failure. Does this then mean that Concorde will enter the history books as the only supersonic civil transport ever to enter service? Perhaps, although British Aerospace and Aerospatiale still conduct research into the feasibility of a larger, more accessible second-generation supersonic airliner. And what of hypersonic spaceplanes and HOTOL? Traditionally, very long-term, very high-tech programs such as these can fall prey to a process of slow cancellation. They aren't axed, they just fade away. If that happens to HOTOL, can we be sure that Britain won't have missed an important opportunity in space?